Hello, my name is Kenneth Chang, and today I'll be presenting Lab 3, Magnetic Field of a Bar Magnet. So for the introduction, the purpose of this lab was to measure the distance dependence of the magnetic field due to a small bar magnet. Then compare our measurements to the distance dependence predicted by the Biot-Savart equations for the on and off axis magnetic fields. So our main results is that n is equal to negative 1.0795. Our K value is 1.892 9 times 10 to negative fifth, and our mu is 91.45 ampere meters squared. So for our fundamental physics principles, we use the Biot-Savart law, which is used to find the magnetic field of a point charge. And the derivation of the Biot-Savart law that we use is the magnetic field of a dipole, which is this formula right here, which is can be used for on and off axis. We then use the distance dependence equations that are given to us in the lab, which are b bar equals kr to the n and ln bx equals ln k plus n ln r. So in the experiment, our system is the bar magnet, our surroundings is everything else, and the initial conditions is the bar magnet and magnetometer. For the procedure, we locate the magnetometer chip inside the phone, measure the magnetic field of the bar magnet on axis, and find the distance dependence and measure the off-axis magnetic field of the bar magnet. So for our observations, we found that the first and last statements are true, and the second and third statements are false. And for our data analysis, the equation from our data is represented by y equals negative 1.0795x minus 10.909. And for our off-axis field, our average distance was 0.123 meters, and our average magnetic net was 3.644 times 10 to negative fifth Teslas. So for our calculations, we use the equation um, that we got from our experiment results, and we set n equal to the slope and ln k equal to the y-intercept, and we solve for k. We then use the formula for a magnetic field of a on-axis dipole and set that equal to the given equation kr to the n. We then calculate mu, and our mu value was 91.45 ampere meter squared, but this value is way larger than it should be, and I explained the errors in the next slide. So some of the assumptions are that the bar magnet is a magnetic dipole, bar magnet has a uniform magnetic charge, and the phone's magnetometer sensor gives accurate and reliable readings. So some of the errors that we could have made where other nearby magnetic sources such as electrons or metals interfered with our the accuracy of our measurements. Also, there could have been a misalignment of the phone, which means like the phone could have been rotated or tilted while sliding it along the meter stick, and this would give us inaccurate readings as well. And we could have incorrectly found the magnetometer location in the phone. So for a computational model, for mu, instead of using the value that I calculated, I used 3 instead to give me a more accurate reading because this is closer to the expected value that we should have got. But due to our errors, we calculated a very much larger value. So this is our function in which we use the formula for the general field, magnetic field of a dipole. Um, Continuing on, we define our position vectors for our magnetic field, and we create arrows, orange ones representing the on-axis, and a sign representing the perpendicular magnetic axis. And we use the function we defined earlier to calculate the magnitudes of these arrows. And then for our distance, we use 0.123 from our data earlier. And we create a magenta arrow to represent our observation point, which is 45 degrees. So this is the results of our computational model. And for the discussion, for the first discussion question, the X component would no longer purely reflect the magnetic field from the bar magnet, as it would be combined with a component of Earth's magnetic field. This would make it a lot more difficult to accurately measure the magnetic field of the bar magnet. And for the second discussion question. I think that the magnitude of the magnetic field and the dipole moment would be larger than using a signal magnet. It would probably be around double since we were using two magnets instead of one.